Computer Organization and Architecture. Chapter 2. Computer Evolution. First-generation computers. From 1951 to 1958, vacuum tubes were used as the primary circuitry for computer operation. This marked the beginning of knowledge about computer technology. Computers from this era include UNIVAC and ENIAC. Computers from this era were often used for business applications, such as payroll, accounting, or inventory control. Characteristics of first-generation computers. Uses vacuum tubes as the main component. The machine is large, consumes a lot of electricity, and generates a lot of heat. Operates using machine language. There was also development of symbolic languages, such as symbolic language and assembly. From 1959 to 1964, transistors were used as the main circuit board, a device developed by three leading scientists from Bell Laboratories: William Shockley, John Bardeen, and Walter Brattain. Transistors are electronic circuit boards that are much smaller than vacuum tubes, but have higher memory capacity, require no warm-up time, use less power, and operate at higher speeds. In addition to circuit technology, other technologies also contributed, such as the creation of computer languages, including assembly language and various high-level languages, such as Fortran and COBOL. Magnetic tape was also introduced for data storage. Transistor-based computers. Second-generation machines. NCR and RCA produced small transistor machines. IBM 7000. DEC, in 1957, produced PDP-1. Third-generation computers. From 1965 to 1970, this era marked a significant shift in computer technology due to the development of integrated circuits, ICs, by Texas Instruments Company, leading to the creation of smaller computers, such as mini-computers. Fourth-generation computers. From 1971 to the present. This is the era of VLSI, very large-scale integration, circuits, in the form of microprocessors. The memory system changed from magnetic rings to semiconductor memory, called RAM, random access memory. This resulted in the creation of personal computers, PCs. Fifth-generation computers, spanning the present and beyond, defined by artificial intelligence, AI, and ultra-large-scale integration, ULSI. These systems utilize billions of densely packed transistors and parallel processing to perform human-like tasks, such as natural language processing, machine learning, and pattern recognition, fundamentally changing how we interact with technology. Beyond the fifth generation, as computing evolves, the line between the fifth and sixth generation blurs, marked by massive leaps in processing capabilities. Quantum computing. Moving away from classical binary bits, zeros and ones, quantum computers use quantum bits, qubits, to process highly complex variables at unprecedented speeds. This promises revolutionary breakthroughs in cryptography, drug discovery, and climate modeling. Neuromorphic hardware. Brain-inspired chips that mimic human neural structures to process information with extreme energy efficiency, solving the impending power crisis of running massive AI models. Edge AI computing. Processing AI workloads directly on local devices, like smartphones or industrial machinery, rather than relying exclusively on the cloud, resulting in real-time, zero-latency performance. An embedded system, often referred to as an embedded computer, is a small computer system designed to perform specific tasks. It involves the collaboration of hardware and software, and is typically embedded within larger electronic devices or machines to control operations and process data. The main components of an embedded system consist of four key parts. Hardware, like the body, comprises the microcontroller, MCU, or microprocessor, MPU, as the core, memory, RAM, ROM, flash, power supply, and other circuits. Software, like the soul and instructions that control the hardware, is often called firmware and is stored in ROM, read-only memory. In more complex systems, an operating system, OS, or real-time operating system, RTOS, may be used to manage resources. Input-output, I/O, is the communication channel with the outside world. Input-output, I/O, the part that connects to sensors to receive values and drive devices to give commands. Connectivity in modern devices often involves the ability to connect to other devices or the internet via various protocols such as Wi-Fi, Bluetooth, Zigbee, LoRaWAN, and CAN bus in cars. The Internet of Things, IoT, is primarily driven by deeply embedded devices, refers to a network of physical objects embedded with sensors, software, and processing ability. These smart devices communicate and exchange data with each other over the internet without requiring human intervention. IoT core components. An IoT ecosystem is made up of 4 foundational elements: sensors/devices, the physical objects that collect data from their environment; connectivity, the network, Wi-Fi, Bluetooth, 5G, or cellular, that transmits this data; data processing, software and algorithms that analyze the collected data to make informed decisions; user interface, applications or dashboards, like a mobile app, that allow users to monitor and control the devices. Moore's Law. It is explained about increased density of components on chip. Described by Gordon Moore, co-founder of Intel. There was number of transistors on a chip will double every year. Since 1970s, development has slowed a little. Number of transistors doubles every 18 months. Cost of a chip has remained almost unchanged. That means higher packing density means shorter electrical paths, giving higher performance. Smaller size gives increased flexibility. Reduced power and cooling requirements. Fewer interconnections increases reliability. First era of memory. Magnetic core memory was popular main memory for computers through the 1960s until it was completely replaced by semiconductor memory. Semiconductor memory, invented on 1970. Size of a single core. For example, 1 bit of magnetic core storage. Holds 256 bits. Non-destructive read. Much faster than core. Capacity approximately doubles each year. In 1842, an English lady named Lady Augusta Ada Byron translated a description of the analytical engine and wrote instructions on how to use the machine to perform complex calculations in her book, Taylor's Scientific Memories. Therefore, Augusta is considered the world's first programmer. She also discovered that the punched cards containing the instructions could be reused if needed. This is the principle of repetition, or looping. The calculating tools developed in the 19th century worked with decimal numbers, but at the beginning of the 20th century, computer systems were progressively developed, leading to a switch to using binary numbers in computer systems, a consequence of the principles of algebra. In 1801, the French inventor Joseph-Marie Jacquard attempted to develop a weaving machine. He used punched cards to record instructions, controlling the loom to follow a predetermined pattern. This approach led to the invention of the punched card machine later on, and it is considered the first machine to use a set of instructions, program, to execute tasks. A 1970s punched card containing 1 line from a Fortran program.